Bachelor of Engineering, Master of Engineering, Doctor of Philosophy as Head of Department, Lecturer, and Researcher at Civil Infrastructure Engineering ITS. The Honorable Mr. Tuan Nghia, Doctor of Philosophy, or Mr. Bill, Lecturer at Geotechnical Engineering Division, Civil Engineering Faculty, Thuyloi University. The Honorable Professor Insinyur Sigit Darmawan, Master of Science in Engineering, Doctor of Philosophy, IPM, ASEAN Engineering, Dean Faculty of Vocation ITS, and the honorable participants of webinar series in this morning. Alhamdulillah, first of all, let's say thanks to God who has been giving us guidance, happiness, healthy, and mercy so that we can attend and participate in this event without any obstacles, even though this event must be held by online. Before that, let me introduce myself. My name is Devita Chandraning Tias as the Master of Ceremony who will host this webinar this morning. This event is the 10th webinar of series in Civil Infrastructure Engineering Webinar Series 2021. This 10th webinar series discusses the topic of design of retaining system of deep excavation in Vietnam cases and experience. Ladies and gentlemen, on this nice occasion, let me deliver the structure of the event today as follows. First, opening. Second, singing Indonesia Raya and Hymn ITS song. Third, opening speech from Professor Insinyur Sigit Darmawan, Master of Science in Engineering, Doctor of Philosophy, IPM, ASEAN Engineering. Fourth, reciting prayer. Fifth, main lecture from the speakers, followed by discussion, Q&A session, guided by moderator. Sixth, certificate submission session and closing. Before going to the next session, webinar participants who haven't filled in attendance can fill in the attendance first, where the link is in the Zoom chat. Entering the next agenda, singing the song Indonesia Raya and the ITS hymn. The audience is asked to straighten their seats and mute the mic so that they can sing the Indonesian national anthem solemnly. The committee in duty is welcome. Next agenda is opening speech. The first speech will be delivered by Professor Insinyur Sigit Darmawan, Master of Science in Engineering, Doctor of Philosophy, IPM, ASEAN Engineering. For Mr. Sigit Darmawan, time is yours.
Thank you for the opportunity to me to give opening speech.
Dengar ya Pak Khoiri suara saya?
Sampun Pak, dengar.
Oke. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah wa syukurillah wala haula wala quwata illa billah. Allahumma sholli ala Sayyidina Muhammad wa ala alihi washabihi ajmain. Good morning everybody. Let me introduce myself. I am Muhammad Sigit Darmawan, Dean of Faculty of Vocational Studies ITS. I'm also one of the lecturer at Civil Infrastructure Engineering Department. First of all, I would like to thank to Tuan Nghia, Ph.D. or Bill, lecturer at Geotechnical Engineering Division, Civil Engineering Faculty, Thuyloi University, Vietnam. Welcome to our webinar series, Bill. It is an honor for us to host you in the webinar series at Civil Infrastructure Engineering Department, Faculty of Vocational Study. I hope that this agenda will be followed by another agendas between the two departments in the future. It's very important to develop our competition, our competence. We are here ready to do joint research, joint publication, lecturer and student exchange between the two departments. Faculty of Vocational Study is a faculty that manages all departments, which has more than 60% practical work in the curriculum. Therefore, it is important for us to have knowledge and experience sharing with practitioner engineers. Today's webinar is one of its kind. The top excavation is very rare, therefore it will be interesting and attractive to the student. I would like to thank to the department for organizing this morning webinar. And finally, many thanks to Tuan Nghia, Ph.D. and to all the students and audience enjoy the lecturers. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Thank you very much, Mr. Sigit Darmawan, for the speech. Next agenda is receiving prayer. For Sultan Ilham, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Before we start our webinar today, let's pray together. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Wassalatu wassalamu ala asrofil anbiya wal mursalin wa ala alihi wa sahbihi ajmain. Ya Allah, companion, forgive us our sin, the sins of our parents, our teachers, Mr. and Mrs. Sins, and the sins of our national heroes who have fallen before us. Ya Allah, the most grateful and merciful, grant to us all a sense of compassion and understanding among us, and give patience to sense to my Mr. Teacher us in educating our. Allah most graceful, give us help, intelligence, guidance, and protection in their studies so that someday we can be useful for religion, homeland, and nation. Ya Allah, the most power, grant us all the knowledge, the benefits, more blessing, and save us from all distress and delusion. Ya Allah, the most skillful, just to prove to us dependent, and only to you we ask for help, the graceful here and application for thy poor servant Nghia. Rabbana atina fid dunya hasanah wa fil akhirati hasanah wa qina adzabannar. Subhana rabbika rabbil izzati amma yasifun wa salamun alal mursalin walhamdulillahi rabbil alamin.
Thank you, Sultan Ilham, who has recited the prayer. May Allah bless us. Amen. Before going to the next session, webinar participants who haven't filled in attendance can fill in the attendance first, where the link is in the Zoom chat. Before entering the main event of today's webinar, let's take a photo. For the audience, you may be able to on cam first, and for the committee in duty, you can help with documentation.
I'm sorry, it's just my turn to relieve my presentation.
Not yet, Bill.
Okay.
They take a photo first. The screenshot. Panitia sudah untuk screenshotnya.
Here we have 6 slides. So we'll take a photo per slide. We're going to start with the first slide. 1, 2, 3. Okay, the second slide. 1, 2, 3. The third slide. 1, 2, 3. The fourth slide. 1, 2, 3. The fifth slide. 1, 2, 3. The sixth slide. 1, 2, 3. Finish. Thank you for the committee in duty for helping us to take the documentation. Next agenda is the main of the event. Presentation from speakers followed by discussion, questions, and answers. Moderator on this webinar will be handled by the Honorable Mr. Muhammad Khoiri, Bachelor of Engineering, Master of Engineering, Doctor of Philosophy, and for Mr. Khoiri, time is yours.
Okay, thank you. Ladies and gentlemen, it's our honor to become a moderator of Mr. Bill or Mr. Nghia Tuan. Before we start, I need to share about a short CV. Mr. Tuan Nghia, now he is a lecturer at Geotechnical Engineering Division of Civil Engineering Faculty in Thuyloi University. He is my friend when he took a master and Ph.D. in Taiwan Tech University or National Taiwan University of Science and Technology. This is only short CV. I think also a lot of work he already done, and maybe not also ongoing project on deep excavation in Vietnam. The next session is we have about 1.5 hours. 1 hour about the presentation and about 25 minutes for question and answer. Ladies and gentlemen, now we're going to the main course of today, the design of retaining system of the excavation in Vietnam cases and experience. With our guest lecturer, Mr. Tuan. Yeah. Mr. Nghia, please take your time to present of your lecture today. Thank you very much.
Okay, thank you, Mr. Professor Khoiri, and good morning, Professor Khoiri and Professor Shizis Damawan, and my friends. Today is my honor to be here to deliver my presentation. Just my very small knowledge on the excavation for the design of the retaining system, and I would like to share my screen. My topic today is the design of retaining system. Design retaining system of deep excavation in Vietnam, just some cases and experience. And this is 6 parts of my presentation. The first part of the introduction, second part of the excavation with anchor work, and the third part that's a variation of anchor load during construction. Here I would like to introduce my small study about the variation of anchor load during the construction. And the fourth part of excavation with prop work. Here I would like to introduce about the work information when we perform excavation using top-down method. And for the fifth part, I will introduce about excavation with batches work. This batches work is quite special because as far as we understand that batches work can help us to reduce the work information. And so I will prove it here. And finally, I have a discussion and conclusions, and then that's the time for answering questions. We don't know that with excavation, the excavation now becomes very popular. Not in Vietnam, among the world. We now perform greater, deeper excavation and with even more innovative retaining system. Many types of retaining wall have been adopted, such as anchor wall, prop wall, precast wall, and batches wall. And in Vietnam now, I would like to tell you that we are adopting more and more the anchor wall because we have a greater excavation. That's why anchor wall becomes more economic, and also it can have a faster construction time. Here you see we have an anchor wall here with 2 anchor layers, and we use Sipil, lesson Sipil as the retaining wall. Here just we do know that wall deformation and anchor load should be taken into account during the excavation because once we cannot control it, we can have a failure of excavation. The left one here, that's one case in Taiwan. That's a very famous case, Taipei Sipil case. And another one that is a case in Vietnam. This is just a pumping station, but that is a large pumping station. And you can see we have a shaft here, horizontal shaft almost bent. It's bent due to the very large earth pressure. And we have a settlement, ground settlement here. You can see ground settlement with crack on the ground surface here. Based on the deep excavation theory and practice book written by Professor Oh Chang-woo, we do know that we have 2 types of wood deformation. The first one that's a cantilever work, cantilever excavation. Okay, cantilever wood deformation. Because this cantilever often occurs if we perform excavation without the retaining, without the prop or anchor. And another that is a deep inward movement. You can see here we have the curve, the curve that's an inward curve of the wood deformation. Besides that, for the ground settlement here, we also have 2 types of ground settlement. That is chop settlement and concave settlement here. And my objectives here just introduce my excavation cases in Vietnam and some lessons learned from them in terms of wood deformation and anchor load. These cases are actually my design projects. That all of them are my design projects. I get involved very deeply into this project, so that's why I know in detail the problem. So I would like to share with you my knowledge about this. Here for the first case, that is excavation, we use an anchor we use anchor work here. You can see this is excavation plan. Okay, can you hear me? Is that clear?
It's clear, very clear.
Oh, okay. Yeah, thank you. This excavation that we have a lot of inclined meter surrounding this, and I actually use 1/4 of this excavation to perform the 3D model and to compare the wall deformation by numerical methods and observation data. Here you just have me to look at the inclinometer number 2 and number 4 here. For these excavations, the excavation depth that is around 10.8 meter from elevation minus 0.8 here to minus 11.6 meter. And I use a Sipil wood. I'm sorry, I use the diaphragm wood here with a thickness at 0.6 meter. And I design the retaining system here, including two anchor layers. With the you know that the anchor here with it contains 2 parts. The first part is the free body. The free body here is 8 meter length, and for the fixed body here, that's 10 meter length, and the spacing of anchor here is 2 meter. Also, we should know that this excavation is performed within the medium clay and also medium dense coarse sand here. Here is the input parameters I use for that. For the second layer and third layer here, I try to use a 8S more model because we do know that 8S models are very good model, especially for sand. But we also want to know how about 8S more. Is that okay to use that? Because 8S more, we know that we have 2 additional parameters like a gamma 0.7 and Z 0.7. So I try to find out what is a reasonable number for them. And here for the second layer here, that is like I use a 8S more model with undrained here, and gamma unset that's 19.2, gamma set 19.5, and E reference here 4.5 times 10 to 4 kilonewton per meter square. And for this, I would like to share my experience that we often use an SPT value to calculate this. E reference, we use an SPT value to calculate this. And for C and phi here, actually for this case, C and phi only adopted from the Narasumber test. And for Z0 here, I select 6 times with 10 to 4 kilonewton per meter square, and gamma 0.7. This gamma 0.7 equal to 1.5 times with 10 to minus 4. Also, this is a value for the third layer, that is the sand layer. And we just adopt that the relationship is for the E50 reference, we take equal to the around double EOED reference, and also equal to 1/3 times with EUR reference. And here we take from an SPT value, that's 4,000 for the clay soil. But for the sandy soil, that is the third layer here, we can see that E50 reference, actually I take around 2,000 an SPT. Because for this, I refer from the study by Professor Benson in Taiwan. And here is how I estimate, here is how I estimate the Z0. Z sub 0 here, that's a shear modulus. The initial shear modulus here, I estimate them from the E value, that's a void ratio. I do know the void ratio for the client, but for sand it's a little bit difficult. So I need to assume that because we cannot take the sample from sandy clients. That's quite difficult to retrieve that. And here, this is the relationship between Z sub 0 and E value. And E value here. And this relationship based on the study by Chmielkowski, 1991. For gamma sub 0.7, the placid success of the values of the range of value is from 10 to -4 to 2 times of 10 to -4. So I take that is around 1.5 in this case. The parameter of the anchor and bore here. Parameter of anchor bore here. We have a bore. Here I use a plate element to model that, and this is a value EI. EI value is 5.85 times with 10 to 5 kilonewton meter square per meter. And for free end anchor here, that's 0.9 times with 10 to 4. Please note that actually for free end anchor here, I try to simulate the free part of the anchor. And for fixed end anchor here, I try to use to simulate the bond length of anchor. Anchor we have two parts. The first part, the upper part, that is the free length, or that only contains the cable. And for the fixed end fixed part here, ground part here, I need to insert ground into the anchor hole. So it will mobilize the friction between the ground and soil. Based on that, we can have a preload or pre-stress to our anchor. For this, the pre-stress, the preload of the anchor is equal to 330 kilonewton and 340 kilonewton, corresponding to the first and the second anchor layers. Here is my model. I use a Placid 3D because we do know that if we use a Placid 2D, only 2D model, we cannot simulate well model. Based on that, I can simulate fully the retaining wall and also the anchor with the spacing. We know that the spacing here is 2 meters. So you can recognize here. You can recognize here for the anchor here. I can simulate each of the anchor here, each of the anchor. And also sometimes with 3D model here, I also can simulate very exactly the excavation procedure. Because sometimes we know that excavation they need time to perform for the whole area. They need to perform step by step, right? Yeah. In order to reach to the final step. So that's why it's also very important when we would like to predict the wall deformation correctly. Here's the model I use have as 100 meter with 100 meter length, and for the depth that's 42 meters. Excavation procedure, you can see here. For excavation procedure, I install Sipil as the first phase. The second phase, I excavate to elevation minus 3.8, and I install the first anchor layer. Then I excavate to elevation minus 6.9 meter, and I install the second anchor layer here. Finally, I need to be water and excavate to elevation minus 11.6. Because for 11.6 here, actually we have the groundwater table. It's greater than groundwater table is greater than our excavation depth. You can see it's here. The groundwater table here is located at elevation minus 8.8 meter. Below is higher than my final excavation depth. So that's why I need to dewater it before I perform excavation. Okay, this is my result. This is my result, my word information. I try to compare between my calculated word information and observation data, and you can see that for the blue, I'm sorry, the green curve here, that word information is the first excavation step. Here, that is the first one, number one here. And for number two, as a second excavation step, we have number two here. It's a little bit greater. But as the final excavation step, actually it increased too much. It's increased too much. My reason for it is sometimes for the final excavation step, the quality of the construction is not really good. They have another additional surcharge. So that's why the word information here actually is increased quite much as compared with the second excavation phase. And my result here for the predicted, this is third one, and it is measurement data. You can see actually measurement data and the calculated data is quite very well to each other. It's close to each other, yeah, right? But only here, as a final part here, we have a slightly different between the numerical result and the measure one. I think the difference here that's due to the case that we cannot we quite use smaller input parameter of the lower part of soil. So that's why the word here is not. I'm sorry, I use the greater input parameters, a little bit different from the fact. So that's why as the lower part here, we have a difference between measurement data and the calculated data. So just small conclusions from this first part. That I have adopted hardening soil small model, and it can predict quite well the word information. And we know that Z sub 0 here can be estimated from E value, because we know that in order to obtain Z sub 0 value here, we need to have a very accurate laboratory test. For example, GISO test with dynamic part, or another that's regional column test in order to get Z sub 0 and also gamma sub 0.7 here. And for gamma sub 0.7 here, I think the range here is quite good. The range here is quite good. So we can assume that. We can assume based on this guideline. Okay, let me proceed to another part. For this part that also very large excavation. Actually, its excavation is invested by Lotte. That's a Korean company. They try to construct a shopping mall here. So they have a very large area. You can see with the area here, they have the width around 200 meters, right? And the length is 300 meters. So the area around 6 hectares, very large one. So that's why for this case, I think it's very suitable to investigate the relationship between very good to investigate the train of anchor load from along the length of the excavation here. Here you can see I examine the point in this range from point A to point H here, and I mark that the value here, that's the distance between my investigated point to the corner. As a corner, we have D equal to 0. H value at H here, D equal to 0. Here. And at A here, this will be equal to L over 2. Here. And here I will investigate the total, that's 8 points. Total is 8 points here. You can see in this table, we have 8 points. I list them here with different D value. Okay, from 0 until L over 2. And in this case, where they have the total excavation depth, that is 10.3 meter. 10.3 meter here. And for the subsoil conditions, they have the first layer, that's a fill layer. The second one, that is a medium sandy clay. And the third one, that is organic soft clay. Actually, this is quite soft. I saw in the construction site, it's quite soft. And we worry about this because they can have a large deformation from this soil layer. Also, we have a medium sandy clay here. Medium sandy clay here. Also, the fifth layer, that's a medium dense sand, dense 5 sand. Medium dense 5 sand. And when we design for the anchor system, we try to put to locate we try to locate the ground part here, the fixed part, into the fifth layer, because we will have a greater friction between ground and soil here. So that's why I locate it here. And for the spacing, I use the spacing 1.6 meter. And then you know that's groundwater table here. Groundwater table, that's elevation minus 6.0 meter. So that's why when I excavate to the final excavation lab here, I also need to dewater. In this case, we use a Sipil type lesson 4, with the length is 16 meter. This is the input parameter of soil. This input parameter of soil, we use a very simple soil model. That's a molecular model. Molecular model here. For the clay soil here, we use undrained behavior to model it. And for the sand, we use drain behavior to model. And you can see that we have a E reference value here. That actually for E reference, based on my experience, E reference here should be equal to EUR, unloading, reloading here. It should be equal to EUR in order to have a correct simulation. So I assume that's equal to EUR here. And for the mu value here for clay, that is from 0.31 to 0.35. Meanwhile, for sandy layer, I use a 0.3 here. And CN5 value here, you can recognize it here for clay. Actually, I take from for clay here. Actually, I take from the triaxial test. We have as a result triaxial test here. So this is a CN5 that in terms of total stress. And only for the fifth line, this is a dense sand, right? So the friction angle is quite large. That's 34. I need to add the dialectic angle. That's a 4 degree here. 4 degree here. Okay. And this is the input parameter of the structural elements. So we have the Sipil core and anchor. For the core, because this is you know that actually for 3D model, we also have a selection, have an option that we only can input E value, A value, and I value. That's why it can help you to calculate EA and EI value. And this is my value here. My value here. A and I take from the catalog by the producer, manufacturer. And for the free part and the ground part here, we know that free part here, I use free and anchor to model that. And for ground part here, I use I use actually I use we can have another choice that's that is zero grit material in plastic. And here is my input parameter. Preload of this case, preload of anchor is 350 kilonewton for each of anchors. This is my model. You see, this model here is just very large. Is that right? Actually, I only model half of them. You can see only model half of the excavation. And due to this very large excavation, that's why you can see the model here is a little bit flat. Although it's very large in terms of width and length, right? But the depth is very, very small as compared with other dimensions. And here you can see this is a half. This is a half of the excavation, only L/2, right? Length over 2. And I investigate this point from H here to A here. H is the corner. And each of investigated point, I will have as a distance D here, the value here. Okay. This is a construction sequence. For the first phase, I will install the wall here. And then for second phase, I have a first excavation. I excavate to 11 minus 2.4 meter. Then I install the first anchor layer. Note that once I install the first anchor layer, I also need to apply the preload for that. And for the second excavation, that is excavate to elevation minus 5.1 meter. As the second, the phase number 5, I will install the second anchor layer. Then I dewater and excavate the third phase here to elevation minus 0.7 to 7.8 meter. Because you know that water here is already greater above the excavation depth. You can see, we come back to look at this. You can see here, groundwater here, that's at the elevation minus 6.0. Meanwhile, we perform elevation up to 7.8, right? So I need to dewater here. This is my total displacement plot. I saw it here. You can see that we have a lesson here. The red one, we have a total displacement that's around 11 centimeters. And for the smallest one, that's 0, right? 0 is located here. 0 total displacement. It means my model is wide enough, large enough to cover all the problem. Okay. And this is my wall deformation. You can see my wall deformation here. For the first excavation depth, this is as the first one. First excavation depth here. Now at this, we have some maximum wall deformation that's around 2 centimeters, right? And this is a kind of a cantilever wall deformation. When I perform for the second excavation step, we know that for second excavation step, we already have the anchor, here, some anchor here. That's why we have this wall deformation. With the upper part is retained, right? It's kept by anchor. And for the third one here, it is the third one. As the third excavation step here. The fourth one here. We also have that the fourth one here. We have the increase. The increase in the wall deformation as the maximum value here is around 5 centimeters. Around 5 centimeters. And you know that it is a wall deformation as the center of this excavation. So that's the large one, the largest point. Okay, it is a very largest point. And this is the relationship between the maximum bore deformation at different points. You know that the point A here is located at the center of excavation, meanwhile point H here located at the corner. So we can know that actually at the corner we have the less bore deformation. At the center we have a largest one. Okay, so I draw the maximum bore deformation with the ratio D over L here. D here, that is the distance. The distance between investigated point to the corner. And D over L, that is the ratio. I would like to have a normalized distance from, you see, the value from 0 to maximum one, the 0.5, sorry. And the maximum bore deformation, you also can see that as the point A here, we have a largest one, right? The largest one here is around 4.5 centimeter. And you can see the behavior of the bore deformation. It increased as a point from corner to the center. And looks like we have the constant of the bore deformation from point D to point A. Is that right? Is that right? Point D to point A. And point D here, that D over L equal to 1 over 8. This here. This here around 1 over 8. So looks like from point D to point A here, we have the same bore deformation, right? So that's why plane strain condition develops from section from D to A, right? But from D to the H here, the corner, we have a corner effect. So that's why we have a smaller bore deformation. That's it. That's quite important, right? Actually, that's also requires with the study by Professor O, but just I would like to reinvestigate to make sure this also works well with the excavation in Vietnam. Okay, and this is the anchor load. Anchor load change with the excavation elevation. And for the anchor loads, I would like to say that it's very complicated. The behavior is quite complicated to predict. Even some case I have I install the sensor attached to the anchor cable tendon, anchor tendon. But the recorded anchor loss looks like it's also it also change fastly. So quite difficult to predict that. Here I just want to say something about this. Just a general trend, maybe different from the experience. At least it works with this case. I have as a, for example, we take a look at the first anchor here, the first anchor layer, right? Take a look at it first. At the first anchor layer, we have a preload here at 350, right? And after we preload that, and it's performed, we have the increase of anchor load here. And then it reduced. Quite surprised, right? It reduced gradually. How can we have that? That's because the second one and the third one. The second and the third anchor layer start to subtract, start to bear the soil pressure. So that's why the first anchor layer they subject to less earth pressure during excavation. And you also can see the same trend for the second layer here. As a first, we have a preload here, and then it increased, right? And then reduce. Also, for the third layer, we also have a chance that increase. But due to it is due to the fact that it is a final excavation depth, so we cannot see more. Maybe if you excavate again, it will reduce. But that is the case if you have another install one more excavation, one more anchor load, one more anchor here. We also will have the same behavior of the anchor load here. So it means it's first of all it increased and then it decreased. Okay. But we should know that the condition for this is we will continuously install the next anchor layer for this step. And I try to draw the anchor load at different investigative point for one step of excavation. Before that, we already investigate for different excavation steps, right? But now only for one excavation step. Let's see what happens. Here I concern about the final one, number 4 excavation step. And during this final one is also quite interesting. You can see for the third layer here. Third layer here we have the increase of the anchor layer of anchor load. Also at around point D here. Point D here, remember that the D over L equal to 1.1/8. I note that here. I note here. At point D. Okay. And remember D is the distance between the center, between the corner and the investigated point. And D over L here equal around 1/8. 1/8. And we will have the constant of the anchor load. So it means that relation shows a very similar behavior in terms of anchor load, not only in terms of body formation. Also for the second layer here, you can see that we have the same. The anchor load almost equal to almost constant from point D to point A. Okay, and then for the first anchor layer, actually for the first anchor layer here we have somehow quite different from the second and the third layer. For the second and the third layer, we have the increase of the anchor load. Is that right? But in the first layer, we have the decrease, the reduction of the anchor load. I just have the reason is maybe that due to the corner effect here, because it due to the groove behavior close to the corner. Close to the corner, the groove behavior, not the groove deformation. That's not only the deep inward movement. Maybe it works the same as the case like a cantilever, a little bit different from the center. That's why the behavior of anchor load here also a little bit different, especially for the first anchor layer. Some observation here. The first one, that's the maximum groove deformation increase when the ratio D over L increase from 0 to 1.8. This is a point H here, a point H here. This is a point D. And then the maximum groove deformation is almost constant from point D to point A. That as a center of excavation. Okay. And within one layer, a specific layer, anchor load firstly increase and then decrease during excavation. But I would like to note that for the first anchor load, they have different behavior. As the final excavation depth here, final excavation step here, we have anchor loads actually varies. It changes, not constant, from 0 to 1/8. And then it becomes constant from D over L 1/2 to 1/8. So it means that actually my plane stress condition will develop from the distance D over L is 1.8 1/8 to the center. That's 1/2 of the excavation. So we can know that actually the 3D the plane strain condition develop within this area. Meanwhile, from the corner to 1/8, 1/8, I mean the normalized distance from 0 to 1/8, we will have the corner effect here. Okay, that's just a very small investigation I would like to share with you. Another excavation I would like to talk, that is would like to talk here, that is excavation with prop work. For this we have a very special one, that is we try to use a precast of the wood. We try to use precast, not Sipil wood, not cast in place wood. we precast in the manufacturer, and then we bring it here and install it. And we would like to know how about its behavior, because you know that once we have we can cast the board in the manufacturer, we can control well the quality. Is that right? And also we can use a very high strength of the reinforced bar. So that's why we can perform for like a pre-stressed concrete components. So we have a greater maximum bending moment. I will show you here. For this excavation, we have the width is around 60 meter, right? 57 meter here, and for the length that's 156 meter here. And we will perform the top-down method here. So that's why we need to have some openings. You see some openings area. We have a total 4 opening areas here, right? And also we have a surrounding inclinometer for this case. Okay. And this is excavation profile. For the excavation depth, that is around 14 meters. We see the ground surface here, elevation is minus 0.45. Meanwhile, the final depth elevation is minus 14.6. So that's why the excavation depth here is around 40 meters. And also we have groundwater table here, located at elevation minus 7.45. And we have the subsoil condition is which is the first layer, that's a fill. This is a fill. This fill here. And for the third one, that is a gray clay sand here. The third one, gray clay sand here. And for the fourth soil layer, that is fine sand here. Because this is excavation in fine sand, so they also need to care much about the watering. And they will use a precast reinforced concrete. You see, precast reinforced concrete wall with the thickness here 50 and 520 millimeter thickness, so around 0.5 meter thickness. But they will have a very large bending moment capacity. You can see this is a borehole here, and the borehole KB2 here. I show you. This is we have a fill, and we have a medium sandy clay with an SPT value around 4. That's a medium. So it's quite a little bit soft here. For the fourth layer, we have a fine sand. Fine sand here, that's quite dense, because you can see the value of an SPT here. That's from 10 to around 20. So it's a kind of dense sand. For the fifth layer, that is a gray clay here. Gray clay here, that's from medium to stiff clay, because we have an SPT that's around 9. And for the sixth clay, for the sixth layer, that also medium to stiff gray clay here. The layer number 6 here, an SPT value that's from 17 to 20. That's a quite stiff clay. Here I show you the cross section of the wall. Cross section of the wall here, we will use a very high strength of concrete, and also we use some high strength of the reinforced bars. Then we perform the preload, and then we cast this beam, cast this wall, and then we cut the high strength reinforced bar here. So we have we did perform tests for this. That's a bending test. We try to perform tests here, and we recognize that the maximum values it can bear, that's around 53 ton meter or 530 kilonewton meter. If we have the normal diaphragm bore cast in place, the diaphragm bore like a 0.5 meter thickness, we cannot have such large bending moment. That's why we try to adopt this, and let's see how it works. Here is my picture from the drone. I took this picture when they perform the final excavation depth. You can see we have a core opening here, number 1, number 2, number 3, number 4 here, and we have a we have a, this is the ramp. It is a ramp to move the subsoil here. Okay, another photo aside, you can see another photo aside here. So okay, this is my input parameters. I try to simulate and back analyze the results. We have a parameter here. Since we have the third and the fourth layer, that is the main layer, they can affect the wall deformation. Okay, just come back to see this one. You see the third, number 3 and number 4 soil layer here. They have a strong effect. They strongly affect our wall deformation. Okay, and this is my input parameters. I try to use another model, that SS model. Here you can see that actually I use quite different models: Marculum, SS small, and SS model. Just also we would like to see how about the result we can get if we use a different model. Okay, and SS model here for the third layer, that is I use a trend behavior for this, and so for the fourth layer here I use a trend behavior also. We have the gamma soil integrate gamma unset and gamma set here, 19.7 and 19.9 for the third layer. And E reference here, I also calculated from an SPT value. And okay, this is values of E OED reference and EUR reference. P reference here, I remain is 100 kilonewton per meter square. And also mu here only 0.5, 0.2. And M value here 0.5 for the sandy soil. And for the C and phi here, friction, I take from the ratio test because I don't have a shared test result in this case. For the fourth layer here, that's a 35 of the friction angle and dilatancy angle. We roughly estimate from the equation is dilatancy angle equal to friction angle minus 30 degrees. Okay, this is a parameter for the core and the slab here. And here, I'm sorry that I don't show the parameter in terms of E, A, and I value. I take all EA value here. I take EA value here, and also EI value here. And for this case, quite special because that's top-down method. So I will reduce the wall stiffness. I reduce 20%. Take only 80% of original value. And also for slab here, I take only around 50% for the first and second, and this is the third slab here. And we have a value here, EA values. The reason why I take only 50% because you can come back to see the opening here. Actually, this opening here, that's they open too much. In my opinion, they open too much. So that's why they can perform the construction faster. But but for the wall deformation is also have a quite large wall deformation as well. And I take only around 50% the capacity of the slab here due to the large area of the opening. Okay, and this is my model. You see, models here is quite complicated because we need to use a plate to model the slab here. Yeah, this slab. We need to use a plate to model this. And also because we use we use a plate to model this, so we also need to draw it very exactly. You see, we have here very exactly the opening area here. Meanwhile, if we use a 2D model, you cannot have this. You cannot have this. And we also have a wall here. We also have a wall here. You see the wall here. Such as here. Apply such as here. Also, with this, I even can model some centerpoles. Because of all top-down method, centerpoles are very important. We use that to support the slab, right? And I model all of them here. So we can model quite well all the components of the structure, of the retaining structure here. For the excavation sequence, I perform total of 8 phases. Number one, that is I install the precast reinforced concrete wall here. And number 2, I excavate to elevation, that's a minus 3.8 meter. And then I cast the first basement, and then I excavate to elevation minus 6.8 meter. Then I cast the second basement here. Then we dewater and excavate through elevation minus 9.8 meter. Then I cast the final basement, and I excavate to minus 14.6 meter. Okay, so you also can recognize that actually we have a quite deep elevation here, as compared with the final one, because for this case we have a quite deep foundation. Foundation here is at least around 3 meters. And some cases which near the center of the building, we even have around 4 meter thickness. Okay, 4 meter thickness of the foundation. Here, that's a micro deformation. Actually, this is not really good at this case. We can see that this is actually this is measure one. Measure one. All of this are measure one. All of this. This is the result for the first, when we perform the first excavation, and when you cast the first slab, and this is for the second slab and the third one here, and this is my result. We have the same behavior. That we have the same curve, the same behavior of the wall deformation, but different in magnitude. Yeah, different in the value of wall deformation here. Okay, so I think I still have some problem I need to take into account, like we can have a more correct the construction sequence here also, and we need to have at least we need to have a very I mean the measurement data from all around surrounding kilometer. Here just for the 1 point, so I need to have more in order to compare this. Just my observation for this case. I recognize that actually, if you can use a precast reinforced concrete wall, it's very good because we can shorten our construction time, and also it's quite I think it's quite friendly environment because why? Once you cast in place the diaphragm wall, you need to have a bentonite, right? And you also need to cast, you need to pour the concrete, right? So that's quite dirty. Quite dirty. So that's why if you have a precast here, you not only control the quality of the wall well, you also can have a friendly environment method here. And also for the top-down method, actually, I suggest that we need to use a 3D model to perform that. Because for top-down method is quite difficult here because we have an opening area, right? So we can model using top-down method here. Okay, looks like I go quite fast, right?
A lot of.
I hope you can get the point.
Very good.
I'm sorry, maybe I can present quite fast.
It's okay.
Okay, yeah.
You can continue it.
Okay, thank you. For the fifth part, here's an excavation with batches work. For this case, my situation is they already have excavation, but they not yet finished. And then they sold this building to another client. And that client asked me, how about the case we will go deeper, excavate deeper, and then help me to design using anchor system in order to retain this. So we have already existing the wall system in terms of diaphragm wall, in terms of the batches wall they already have. And now they try to excavate more. And then when they excavate more, we need to install the anchor system here in order to maintain the wall. Yeah, so that's a quite difficult situation. And in here you can see that we have the main wall here, from this to this, from this to this. Yeah, we have the main wall here. Yeah, but actually we for this we also have the batches wall here. Even some cases you see as this case, they have batches wall that's outer batches wall, not inner. Most of them are inner, but some cases here they even have outer batches wall, and they will demolish part of this batches wall when they finish the construction. That's why my job becomes more difficult. For example, they have, you see they have a circular here, right? A circle here, right? Actually, that's a ramp. That's a circular ramp for the car parking. They will use it for car parking. And once they construct this ramp, they need to demolish. They need to demolish some parts of the batches wall here. That's why we need to take into account this problem also. And for the in terms of dimension, we have this direction. The dimension is 75 meter, and for this is 63 meter. For this are 63 meter here. So okay, and just this is the photo side. You can see we have a main wall here. And we have a batches wall here. All of this, they have a thickness equal to each other. That is 0.6 meter. And you see, they also even have some slab here. Second, they have a two slab area. And for this slab area, they also will demolish after they finish. And here you see this for this guy actually is close to the hill. We have a hill here. As this part they also need to construct the building. So that's why they need to have retaining system for this hill also. And here you see the retaining system. And we have excavation here. Okay. Now, just some introduction about the machine, how to install the anchor for this. Because you see that if we use a normal anchor, a normal machine, drilling machine, we cannot perform the building for this case. That's why I need to adopt this is a kind of sky drilling. This sky drilling, I will use a crane here, elevator here, right? So I will have a machine here. They need to lift up this machine, and this machine will perform drilling here. You see, this is excavation profile. This This guy is very complicated, so I would like to say with you more. For example, we have a D-word here. The top elevation is 24.5 here, and the bottom elevation is only -3. So the total length here is around 27.5, right? But they need to excavate very deep. They need to excavate here, that is 0.7. From 24.5 to 0.7 here, that's around 34 meter, right? 34 meter. And they only have the penetration depth from 0.7 to -3, that already around 3.7 penetration depth here. That's a very shallow one. And we have a budget score here. Budget score, this is a budget score here. For this budget score, actually, it also is not constructed from the top of the diagram board. That from the elevation only 12.75. And then they will demolish some of this budget score. And you see, this is the existing elevation that's 5.0 elevation. You can see from this photo here. This also the elevation of already 5.0. 5.0 here. Already 5.0. And they will excavate more from 5.0 here to 0.7 in order to reach the foundation elevation. And for this guy, I need to adopt the 5 anchor layers. 5 anchor layers. This is number 1 here, number 2 here, 3, 4, and 5. Because you see that existing level already is 5.0, so that's why I can install 4 above anchor layer immediately. After I finish installation of these 4 anchor layers, I will excavate to the elevation here, that's 4.0. And after I excavate to this, I will install the 5th layer, and then they will go further to the foundation level. And then after I finish, I will demolish all of the budget score and slab. Okay, that's just a rough overview of this excavation. In terms of the subsoil layer here, we have for the subsoil layer here we have a total of 6 type of soil. For 6 type soil here, the number 1, that's the field. Number 1, that's big field soil, yellow, gray, and yellow brown, silty clay. You can read it here. And for the second, the layer number 2, we have that yellow brown, also pink brown, steep to semi-steep. Steep to semi-steep clay. And for the third layer, 3A here, we have that is a red brown, also semi-steep to steep clay, and mixed with gravel. That's very hard one, But it also due to it's very hard and it's mixed with gravel. So that's why it caused a problem for the construction for the contractor. Because when they drill the anchor hole, drill a hole to install anchor. Okay, and they think that they observe that the gravel here always fall down to the hole. That's why they need to use a stabilizing fluid like a bentonite to stabilize the hole. Okay, and we have a T-gain 3. This is the layer. This is a kind of limestone, really limestone, strongly weathered and cracked. Strongly weathered and cracked here. For 3A, this layer also 3A that are from steep, semi-steep to steep gravel here. Other 14, number 14 here we have that's a red brown with that semi-steep to steep clay and also with gravel. with gravel and rock here. Okay, so the overview that we have as the overview observation is the subsoil here is quite good. It's quite good, not quite steep, but it's very difficult for the construction, so for the installation of anchor. And I have another observation is, you can see that we have a adjacent building here. That's it. This is a cross section number. This is a cross section 11. You see, cross section 11. I would like to introduce you only this cross section to see the difficulty of this buildings. Okay. You see, this is a 11, right? Cross section 11 here. Cross section 11 here. Cross section 11 here. And we have some ball pie here. We have some ball pie here. Some ball pie here. You can see this is a circle, right? The right circle here, that is a ball pie. That is ball pie. So that's why when I design for the anchor, I need to overcome this difficulty. That's I need to have a very good layout of the anchor. Okay, can you hear me?
It's clear.
Okay, okay. I need to have a very good layout of the anchor. We need to try to avoid crash with the ball pie. And here, in order to model that, okay, I'm sorry, I go to the soil condition first. This is a borehole profile. This is a borehole profile I would like to show you. Borehole profile here. We have a field here. First layer field here with a depth of 4.5 meters. And layer number 2, that is a yellow medium to thick sandy clay. That's a 9.6 meter thickness. And Thuyloi here, that is a 3.8 meter thickness here. That's brown steep sandy clay. And also TK3 here, just repeat it to help you get information. TK3, we have a limestone here, and RQD value is only 10%. So that's why it's quite this is a strongly weathered rock. The thickness is 2.9 meter. And for the Thuyloi here, that is 10.6 meter. 10.6 meter here. That is steep sandy clay here. You also can see the SPT. We have a SPT value here. SPT value here with the number 2. That we have the SPT values that's from 14 to around 38 meter, 38 value. And for the layer 3A here, that's also quite large. An SPT value, that's a 32. That's quite large. And for the limestone here, actually we cannot perform the SPT value, an SPT. And for 3A here, we see an SPT values from 14 to 32 here. Okay, and this is my input parameters. This is my input parameter. This is my input parameter. We know that for the second and the third layer, actually that is they are the main soil layer here. So I would like to show you the input parameters of this soil. Okay, you can see from the excavation profile here, the number 2 and number 3A here, they are the main soil. We will find out what information. And for the input parameter, you see, I use a HS model with undrained here, HS model undrained here for both two soil layers. And gamma unset and gamma set here equal to 20 and 21. E reference 50. E50 reference here, I take a 1.83 times with 10 to 4 kilonewton per meter square for the second layer. And for E reference here, Actually, in reference here, I take it equal to E50. And for the EUR reference here, I take 3 times of E50. 3 times of E50 reference here. I remain the value for P reference at 100 here. Mu I equal to 0.2, mu R here. M values as 1.0. And for C and phi, we also have a triaxial test here. So we take the C and phi from triaxial test. That's the total parameters. And for the SS model for the third layer, here we have for the third layer here, gamma unset and gamma set equal to 20 and 20.3. And for E reference, that is 1.31 times with 10 to 4 kilonewton per meter square. And also we take the EUR equal to 3 times of E50. Okay? And this is a value of C and phi. We have this. Also, we have a friction angle here. You see that 38.5. So that's why I have relative shear angle that's around 88.5, because I will estimate from the friction angle minus 30 degrees. This is a parameter of the Bacchus-Wohl and diaphragm-Wohl. And since we have a Bacchus-Wohl and diaphragm-Wohl here have this similar thickness as 0.6 meter. So I have an input parameter of EA and EI value here, 4.7 T7 times with 10 to 5 kilonewton meter square per meter. That's for the diaphragm here. And EI value, that's a 1.59 times with 10 to 7 kilonewton per meter. Here is my model. That is a 3D model. You can see that that's a 3D model for the cross-section 1-1. You can come back to see cross-section 1-1 here. It is section 1. It is a cross-section 1 here. Yeah, I would like to model it. And you see, this is finite element model. And I need to model the slab here, some Bacchus-Wohl here also here, and due to this corner, I need to fix the wall deformation also, because we know that as a corner the wall deformation is very small. So in order to reduce the model, I only model this part of the cross section. And you can see we have very many ball pipe here. You see, so many ball pipe here. So that's why I need to have a very good layout of the anchor. Otherwise, it will crush the ball pipe, right? So you can see that here, it's a very difficult one. Also, this is excavation sequence. For this, we, as I said before that, since we have a 4 above layer here from the anchor layer from 1 to 4 here, it's already located. They are located above this existing level 5 here, elevation 5.0 here, right? So that's why I can install the 4 anchor layer first, and then I will need to excavate before I install the anchor layer number 5 here. So that's why my excavation sequence is I install anchor layer number 1, 2, 3, 4 first, and then I excavate, to elevation 4.0, and then I install the number 5 anchor layer, and I excavate more to 0.7. That is the final one, and I will demolish some Bacchus-Wohl after I excavate it. Okay, and you can see this is a wall deformation as a final excavation stage. Here you see I already demolished some Bacchus-Wohl here, and I have I have as a word information. Thus, I'm sorry for this case, batches will not are not demolished. Remember this, are not demolished. Here you can see excavate to elevation 0.7, and then I will demolish. Okay, and before I demolish, I have as a word information is around 6 centimeters. Okay, after I demolish, you can see it become 9 centimeters. Quite large, 9 centimeters. Even though we have the total excavation depth is around 20 meters, right? 24 meters. That also very deep one. But 9 centimeters, that's even that's still within our limit value. But I think for the word information, we should not exceed 10 centimeters word information. Otherwise, you have some panel here. It will have a gap between the panel, the whole panel. Here you see the total length is the total displacement horizontal one that 9 centimeters. That is after I demolish batches work. After I demolish batches work. So that's why we can see that actually the effectiveness of the batches work here is significant in terms of word information. My conclusion is installation of anchor here will be restricted by the existing buildings, so that if we want to overcome this, only 3D model can help you to solve. Okay, because sometimes we cannot have a very good construction site. We cannot have a very how to say, very easy work for you. You also need to encounter some problems, and this is very tough problem. And we need to use 3D model in order to install the very good layout of anchors. Also, I recognize that the existence of batches work affects significantly the word information. Once you want to read, once you demolish it, you can cause the word information. Okay, and this is a discussion and conclusions based on the 4 case study. I have some observation here. First, with SS small model, we also can predict quite well the word information with this, but Z sub-0 here, we should estimate from the void ratio E value. And for gamma sub 0.7 here, the range value of this up from 10 to minus 4 to 2 times 10 to minus 4 here. And this is, I think this is quite reasonable range for us. For the plane stress condition or 3D condition, I have the conclusion is maximum word information actually increase if D over L increase from 0 to 1 over 8. Just a small reminder to you that that D is the distance between the corner and our investigated point, and L that is the length of our excavation. So if D over L increase from 0 to 1 over 8 here, we will have as a constant of the word information. But I'm sorry, we will have an increase in the word information. But if we have greater values as from 1 over 8 to 1 over 2 here, our word information is almost constant. As the final excavation state here, for the final excavation state, we will have the envelopes actually change, varies from D over L equal to 0 to 1 over 8. And it will be constant. The envelope is constant from if D over L from 1 over 8 to 1 over 2 here. Okay, so it has a connection between the envelopes and our word information. We can recognize that, right? For the case we use a precast reinforced concrete work, I think that should be the technology of the future, because in the future, because why? We will have a very good environment if we adopt this technique. And also we can have a larger bending capacity of work, because we can compare between the wall within the 0.5 meter and that is a cast in place wall and the precast wall. We have different in terms of capacity. Okay, and also we have a different we have a different quality among them. So that's why I suggest that if possible, we should adopt a precast concrete wall. And we see that existence of buttress wall here that strongly affect our wall deformation. So that's why in some cases, if possible, you can contrast the buttress wall here in order to reduce the wall deformation. Because I do know that in Taiwan, actually they adopt properly buttress wall, but in Vietnam, actually not too much. I even try to install this in design this in some cases, but the clients still not have confident enough. They are not confident enough to adopt this. They worry that maybe the construction quality is not good, so maybe they have the gap between the buttress wall and our main wall, and even buttress wall here and main wall, if we cast in place in one piece, one panel here, they also worry that it's too heavy to perform. So, a lot of reasons, okay, and even so, even they worry about how to demolish, how it affects the main wall if we remove the buttress wall. So that's why I still have a reason they don't want to adopt. Anyway, I still believe that if we adopt the buttress wall, we can reduce the wall deformation too much. So that's very good. I think that's a good opportunity to try. Thank you very much. And this shows my photo, my memory with Professor Mohamed Khoiri. That's just when I was young, right? And he also was young. Now we different.
Yeah, looking tiny today.
Yeah. Also, this is my photo when I reunite with Professor O in Ho Chi Minh City. We have a conference there, so I met him. I met him at that time. Okay, then thank you for the listening. And if you have any questions, feel free to do that. Okay.
Okay. Thank you very much, Dr. Bill.
You're welcome.
Yeah. Every in an offline meeting, you'll get a very big applause here. Before we go to question and answer, maybe I will read some of brief conclusion there. Mr. Bill already present it in very excellent, interesting, inspiring. He present a great 4D excavation project in Vietnam, I think 4, yeah?
Yes.
With a lot of information there, a lot of information there, and very useful for us. The variation of technical aspect point of view that already has been presented involve soil parameter determination, 2D and 3D plexus model, wall deformation and 3D effect, also how to determine several model like MC model, is SR, is SS. He also explained his experience in strat load, ground anchor load versus depth of excavation. Also the last about the precast wall, and also a complex structure of construction of the excavation that involve buttress wall, opening slab, also ground anchor. Very excellent. Now we already have 1-2 question in chat room. Maybe I will ask other participant to ask directly to you, Miss Fira.
Yes. Yeah, I'm here, Dr. Khoiri. So good morning, Dr. Bill. Thank you for your great lecture in this morning. My name is Firda. I am the postgraduate student of Dr. Khoiri. And in this session, I want to know how to determine the dimension of our model. So we can make sure that the extra area, like in the wide, the large, like the length and the width and the depth, something like that, big enough to cover the effect of like maybe like deformation, something like that. That's my question. Thank you.
Thank you. Okay, so Ms. Frida, I would like to explain how to have a reasonable dimensions like this. For example, you see after every model, I often check the total displacement first. For the total displacement, we can have a choice that we have options that we can show the lesion, the shading area here. You can see because shading areas can show you roughly the deformation of all the soil and the wood, right? You can see for this blue one, the wood deformation almost zero here, or soil deformation, I'm sorry, almost zero here. So you can check it here. So we have a zero around this, right? This area, and also zero here. So we will get the confidence that we will have enough model dimensions to cover what we concern, that is the wood deformation or even ground settlement. Yeah, because after, if you, for example, if you have a smaller deformation, you will have this, something like this. Yeah, if you have just this model, you can see that the deformation already reached our boundary line. Okay, you can change this. So if you feel that it reached our boundary line already, for example, in here, that's maybe the right boundary, I will enlarge this. As long as I get the correct total displacement plot here. Okay, so at least we should make sure we have a zero deformation of soil in this area. So it means that the deformation of soil and wood already developed well. It's not restricted by our model dimensions. Thank you.
So like we should like kind of trial and error or something like that?
Yeah, okay, that. And just for example, if you want to have a good estimate, not too many trials. If we perform too many trials, we also feel tired about that, right? Yeah. So in my opinion, for large one here, at least it should double this area of the work. This area, excavation area. So for example, I have over 2 here. I will take at least this. Another function is we should try with the depth, excavation depth. For example, we have a HE value here. In my case, I've often adopt at least four times of excavation depth. Why it should be 4 times? Because I recognize that the radius of the failure surface, at least for soft soil, is equal to around 2 times of excavation depth. So I take 4 times, I can cover double radius of failure surface. So that's why I can have a very good model. Just my experience.
Okay, thank you so much, Dr. Bill. I'm sorry.
Frida, we as appreciation, maybe we can take the screenshot of you, Mr. Bill, and me. Mr. Bill, you can stop share for a moment, please.
Okay. Is that this? Oh,
stop sharing.
That's what you mean.
Stop sharing the presentation. So the panitia mungkin Firda bisa dipin lagi ya, nanti biar screenshotnya bertiga gambarnya. Bill, you can stop sharing your presentation. Yes.
Okay, sure. Okay.
Then we have 3 of us. We can take a screenshot with the participant with the question. Okay, thank you. Thank you, Vidra. A second question already there. You know who, Mr. Bill? There is Aswin here. Aswin, please.
Okay, good morning, Dr. Bill.
Okay, Professor Aswin.
Hey, Professor.
No, Mr. Khoiri, Dr. Khoiri doesn't tell me about you.
No, I just see a broadcast in WhatsApp after my class, and then I just joined this very fruitful talk from you, Dr. Bill.
Okay.
Okay, then just go to the question, okay?
Okay.
Okay, please advise how to determine the slab opening area, because in Jakarta, Bandung, when we design the top-down construction, we also need the slab opening, right, for the excavator to excavate. And then this will also become debate from the consultant and the contractor. Contractor want the large size of the slab opening, but consultant is afraid that the area will affect our slab system stiffness. From your experience, what is this area ratio for? Is the ideal area ratio so that the slab opening not affect much for our slab system?
Yes.
This is number one, but for number two is I take it for the rest. Okay.
Yeah. That's a very interesting question, because actually not in your country, in my country, they also debate for that. They would like, they have the controversy between the contractor and designer.
Yes.
Because contractor always want to have the opening as large as possible. Yes. They can push up the construction hub. In here in Vietnam, if we open that, we will reduce the slab stiffness, right? We will reduce the normal stiffness, and we will estimate the wall deformation based on that. And we will have the limit value for wall deformation. That's also the same as in Professor textbook, that over from 0.2 to 0.5%. The wall deformation, we will limit that from 0.2 to 0.5%. To 0.5% here. And we also need to check another. That is, we cannot allow the maximum wall deformation of more than 10 centimeters.
10 centimeters.
10 centimeters cannot have the greater than 10 centimeters, because the goal is that for the wall we have a panel wall. For each segment here, if they have a differential settlement deformation, they can have a gap between them. So the groundwater table can time. Yeah, so they worry about that. So they have at least these two criteria. And of course, the third one, we need to check about the bending capacity of the wall. Once they think that the bending moment here is greater than bending capacity of the wall, we will not allow that.
Oh, okay, yes, okay.
Yeah. Okay.
Okay.
And also just another discussion with you that actually in Vietnam, top-down method nowadays we don't use this properly because it has problem. You see that excavation here, we cannot perform excavation once for all, right? We need to excavate just step by step. So that's why actually the slab here, all of the slab here, they will have a different deformation. Sometimes they distort. So that's why this corner, we always have the crack of slab. That's very difficult to deal with this problem, because for this problem we need to have a reinforced archive textile. I don't know exactly the name, but they need to treat this problem. So it's also not convenient to do that. So that's why in Vietnam now they often use the anchor.
Anchor.
Especially for the new buildings or the newer city, they prefer that. Okay, thank you.
Okay, thank you, Bill.
Thank you. I already take a photo, 3 of us. Then you can send in
Send
Facebook.
to your boss.
Okay,
The boss.
Send
thank
to
you.
your boss.
Yeah, thank you very much.
Thank you very
Really nice,
Okay, thank
enjoy
you.
photo. Thank you.
Maybe it's already 1 minute from 11, but maybe one question more is okay. Please, if there is one question more about the deep excavation in Vietnam.
Okay.
It looks like nobody asking in the chat. Could I ask one, Mr. Bill? Dr.
Okay,
Bill?
okay, you're welcome.
Okay. Yeah. As I know, you already examined the safety factor of deep excavation using numerical method at your last thesis. Have you implemented that approach for deep excavation at Vietnam, or maybe you can you have some note of that method?
I'm sorry, I cannot follow the point. You made a factor setting, right?
Yeah. First, usually we calculate factor basal heave or push in manually, right? And you have study using numerical method. Have you implement that numerical method in your project in Vietnam?
Yes, of course. Because once let me tell you this. Once we design for this, first of all, we care about the body information here. Number 1 here, number 2 here, and also the bending moment itself. And number 4 here, we care about the factor safety. We care about factor safety. But my experience is factor safety calculated by plastic looks like it's greater than the hand calculation. For example, if we use factor safety by Professor O for slip circle method equal to, for example, equal to 1.2. For example, we have this by slip circle method here, that equal to 1.2 here. But if I use plastic, it's always greater than this, around 1.3 or 1.4. That's why sometimes if we, I think that's a disadvantage of numerical because numerical here, they don't reduce the strength of the wall stiffness together with the C and phi value of soil. So that's why we have this problem. Yeah, so that's why in my opinion, if I adopt the numerical result, I often take the factor safety around 1.3, at least 1.3 here. Yeah.
Okay. Thank you very much, Dr. Bill. Okay, now we already end of this lecture session, question and answer. And please give a big applause for Dr. Bill. Thank you very much. And now this time I offer to the MC what's the next of this agenda. Thank you very much.
Okay, well, thank you very much to Mr. Khoiri as the moderator and also Mr. Do, Tuan Nghia, or Mr. Bill as the keynote speaker for being willing to fill out today's webinar. Previously, there will be a certificate submission which will be represented by Mr. Khoiri. The committee in duty can be helped by sharing screens.
It's very nice.
Thank you very much, Dr. Bill. Yeah, please accept our appreciation for your presentation today and for your very great lecture and your sharing session. Thank you very much.
Thank you. You're welcome. Yeah.
Before we end today's webinar, let's take a photo. The audience may be able to on cam first, and for the committee in duty, documentation can be assisted. Okay. Here we have 7 slides. So we'll take a photo per slide. We're going to start with the first slide. 1, 2, 3. And the second slide. 1, 2, 3. The third slide. 1, 2, 3. The fourth slide. 1, 2, 3. The fifth slide. 1, 2, 3. The sixth slide. 1, 2, 3. And the seventh slide. 1, 2, 3. Finish. Thank you for the committee in duty for helping us to take the documentation. Before going to the next session, webinar participants who haven't filled in attendance can fill in the attendance first, where the link is in the Zoom chat. Alhamdulillah, we have reached the end of the event. Thank you very much to the speaker, moderator, and participants who have listened to the event from beginning to end. Hopefully, a lot of knowledge gained to be applied in everyday life. See you in the next webinar series.
Thank you.
Thank you, Mr. Bill. Dr. Bill.
Thank you.
Maybe in the future you can go to Surabaya.
Okay. If you have a preference there, just let me know.
Yes. Okay.
Yeah, it's my honor to attend there.
Yeah.
Okay. Yeah. See you.
Yeah. Thank you very much.
Yeah. Bye bye. Thank you very much.
Thank you.
Yeah. Bye bye.
Okay. On behalf of the committee in duty, I apologize for the wrong words and actions. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih panitia, Bapak Ibu dosen panitia, Mas-mas Mbak-mbak mahasiswa panitia. Selamat siang Pak Heri, ini muncul juga di sini. Terus sangat.
Selamat siang Pak Khoiri.
Selamat siang Pak Kunjoro.
Ya, saya pamit dulu. Pak Khoiri, Bu Kamil, dan seluruh panitia, terima kasih saya ucapkan.
Sama-sama.
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi
Ya, saya izin live dulu ya, Mbak-mbak, Mas-mas semua. Terima kasih banyak. Panitia nanti selanjutnya koordinasi di grup chat WA. Bu Kamilia, matur suwun, saya pamit dulu. Assalamualaikum.
Bapak Ibu, saya izin